All right, this is a demonstration of the Agilent 400 system run in automation mode. The first thing you should do is make sure your sample is depth gauged properly. So insert your NMR tube onto the spinner and then place it in the depth gauge and press your sample all the way down. Make sure that's set properly. Then once your sample's ready, come to the NMRJ and click eject. Once you click eject, you should hear the eject air blow out easily. So if you're not hearing the eject air, you should check with staff. If you drop your sample in without the eject air on, you can easily crack or break your tube. So once you click eject, you should hear the air blowing out. Take your sample over to the top of the stack, set your sample in the stack, and it should float there easily. Once you have your sample in, come back over to the computer, click insert, and it lowers your sample down in slowly, and you can usually hear it click at the bottom once it's down at the probe. All right, once your sample's in, a good habit to make is to come over to the Start tab here, and then click on shim, and then click Read Default Shims. And we have a set of shims saved for a standard chloroform sample, and that will save you some shimming time if the person before you had a very short sample or a very different solvent, and it'll go through more shim cycles when you have very different shims from yours at the start. That loads the numbers into these settings here. You have spinning shims and then non-spinning shims, so it gives you a good starting place. So once you have the shim file loaded, then you want to queue up all the experiments that you want, and that'll happen in this window here. So click New Study, and you'll see that it says New Sample now, Sample Info. And under Sample Info is everything in this tab here. So you want to put in a sample name, a file name, and it should be letters and numbers, no spaces. If you want a space, you can put in an underscore. Then enter your solvent. You have the three common solvents here: DMSO, chloroform, D2O. If you have a different solvent, you drop down menu here, and there are a number of other solvents you can pick from. Once you have your file name in, solvent entered, then you can start adding to the queue the experiments that you want to run. So for today, we'll just run a proton and a carbon, and you can select from the buttons here for the most common experiments. You have proton, carbon, a few 2D here. The exception for that don't appear on the common page are fluorine and phosphorus. You go to the liquids, click the drop down, and you have fluorine, you have phosphorus. You also have depth experiment here that you only want to run occasionally, but most everything you want is on the front tab, first tab here, common experiments. If you do select an experiment that you, by accident, you don't want, you can delete it from the queue by right-clicking on it and delete. Now, to change any of the parameters with any of these experiments that you have in the queue, you just double-click on the experiment. It loads the parameters in for that experiment, and under defaults, the most common things, you have your sweep width, because that's your left and right endpoints. -2 to 14 is good for most proton spectra, but if you happen to have a very negative peak, you can change this to -10 or move to a more positive peak with this entry here. Most commonly, we change the number of scans. So I think most protons for concentrations from 5 milligrams on up shouldn't need more than 16 to 64 scans on the 400. Relaxation delay default is usually pretty good for most organic things, 2 seconds. Another parameter that's good to know about is the acquisition time, which is 4 seconds. And that's a default. So That's a pretty good default for most samples. So if you want to change the number of scans for carbon, double click on the carbon and those parameters are loaded. You have the similar parameters here. You have endpoints. You won't have to change very often for carbon. Number of scans. Carbon's much less sensitive than protons, so you're always going to need more scans for carbon. Usually plan on at least 15 to 30 minutes for something that's 10 milligrams or more. Start getting very dilute samples, less than 5 milligrams, you need to bring it to the Prodigy 500 cryoprobe so you can run it quickly. So on this sample is very concentrated. I'm only going to need 16 scans. Relaxation delay defaults 2, and the flip angle defaults 30 for carbon. It's also default is for proton is 30-degree flip angle, and those are fairly conservative numbers for most organic things. The new parameter you have in carbon that you don't see in proton is decoupling information. So you're going to be decoupling while you're acquiring, decoupling protons while you're acquiring carbon. That makes your carbon signal a singlet instead of a multiplet, and that enhances the sensitivity considerably. So if you look at the main display here, it gives you the pulse train for this experiment. Across the top is what's happening on the carbon channel. The bottom is what's happening with the proton channel. So on the carbon, you're seeing the relaxation delay of 2 seconds, your pulse width, and 3.2 microseconds happens to be 30-degree flip angle for carbon. And then you got 2 seconds acquisition time. So on the proton, you're running decoupling the whole time. It's decoupled during the relaxation delay and decoupling during acquisition. So the decoupling during acquisition makes the multiplet a singlet. The decoupling during the relaxation delay is the NOE. So that part gives signal enhancement for any carbons that are coupled to protons. So the more protons you have on a carbon, the taller the signal usually is. So usually your methyl carbons will be taller than your methynes, and your quaternary carbons will be the shortest of all, but they also are a little shorter because the relaxation time is much longer. So this was the default and the selection you should run with most of the time. But you can see if you run decoupled minus NOE, you still are getting a singlet, but you're not getting the enhancement for decoupling during relaxation time. So your sensitivity will be less. So this is the default is a good setting. Your acquisition time for carbon is usually about 2 seconds, and that's under this selection here. So you've changed several parameters. So to look at the total time for the experiment and the time for each individual experiments next to the name for that experiment. When you change the parameters to update this information, you click show time. So now it's the proton and the carbon are both going to run about a minute. The total time for the experiment is going to be 4 minutes, but they have some additional time put in there for shimming. So everything's pretty much ready now. So you go down to the submit button, click that. It takes a few seconds to start. So now your queue window changes, and if you click spectrometer, then you're going to see a new directory related to the date. If you expand that directory, you'll see active study, completed studies. So under active study are the 2 experiments that you're running, and this greenish color is a sample, the experiments running currently. Completed studies are the things that you've run previous logins. So in this window, small window at the very bottom, it's telling you what's going on at that time. It's trying to shim now. A shim cycle is about a half a minute. It usually goes through about 3 cycles to shim. This window here, a small window, is for errors, so hopefully you won't see anything there. So it's still going through a shim cycle. Like I say, it usually takes about 3 cycles to get through it. If you have to stop the experiment at any time, if you've forgotten to change a parameter or something like that, it's better to stop it with not with by clicking the stop button here, but go to automation, background, and then you got several selections for stopping here. And these usually are less likely to hang the system up than just clicking the stop button. If you click stop, say resume at this point, it would stop the proton, but then start the carbon. So you'd have to do that a second time to completely stop everything. So that's usually the best way to stop it. Automation, background acquisition, and then choose one of these. So now it's finished shimming and it's trying to regulate the spin. And so it's spinning up to 20 revolutions per second. Spinning gives you a little bit better resolution than non-spinning. So it's an advantage on some instruments. Some of the newer instruments, there's less difference in spinning and non-spinning. Now it's locking. It did that quickly. Indication of the lock level is here. It's at 100, so it's locked fine. Now it's counting down on running the proton spectra. It's about a minute. And once it's finished and these two change colors, you can double click on the proton and look at your proton spectra while your carbon's running. It's always a good idea to look at the proton before you take your sample out and make sure the shimming went well. So when it finishes, we're going to look at the chloroform and the TMS signal and make sure that they're not split or they're very sharp and a symmetrical peak. If it's not, you need to try rerunning it again. Some of the common problems for bad shimming are your volume's too short. You got solid floating in your tube, or you've not depth gauged it properly, or mixed your sample properly. So those are all things you should check if your shimming's not good. So it's finished, and now it's running on the carbon. So we're going to double click the proton entry. Auto processes your data. To look at the chloroform signal, the signal here at 7.2, you can click on your left mouse button, gives you a cursor, right mouse button, a second cursor, and then you can drag that around with the left mouse and zoom in on the chloroform peak, and then click the zoom icon here on the right. So you should be seeing a nice sharp singlet, sharp peak at the top, not split, not misshapen with a foot off one side or the other before you take your sample out. If you have TMS, it's even a better way to look at your shimming. You can also look at the top, make sure it's not split. But you also with TMS, you have silicon satellites. So silicon has a spin of a half, but it's only about 4% of the silicon. So if it was 100% spin of a half, TMS would be a large doublet. But now you're seeing a doublet at somewhat less than 4% of the height of the main peak. And that coupling is about 6 hertz. So if you're seeing sort of resolve close to the baseline between the main peak and the silicon satellites, your shimming is very good. As your shimming starts to get poor, the base starts drifting out and will cover up these peaks. That's a good indication of how well you're shimmed. So this one went well, and that's, like I say, it's always a good thing to check. Once your both experiments are finished, then your display over here in the Q window changes again. You can expand the directories. The active has disappeared, and you just have completed. So down at the bottom of the list, you should be able to see the sample and the name you gave it before you started. You can expand that directory, double click on proton and look at it, double click on carbon and look at that. So you can see pretty quickly that the carbon is much less sensitive. For the same number of scans, your noise levels, a good 20 times more that of protons, probably even more than that. So carbon's much less sensitive, so you keep that in mind when you're collecting data. I found a good judge or a good marker for running carbon, and you run your proton. And if your peaks are smaller than your chloroform peak, you're not going to be able to run it in a 30-minute run on the 400. So in this case, as long as most all your peaks are the same size or larger than your chloroform and proton, you can often get a carbon spectra in a half hour. Once they get smaller than the chloroform, you should move to the Prodigy 500 for a carbon. So both of those ran well. So you're ready to take your sample out and log out. First thing you do is go over to the Start tab, lock, make sure the spinning's off. Right, it shouldn't be a check mark there. Check the lock. So now that there's no check mark on either, the spin's off, the lock's off. You click eject, and your sample should float up to the top of the stack. Take your sample out carefully, so lift all the way up and make sure the bottom of the tube clears the stack before you walk away. It's a common problem. When people get in a hurry, they lift their sample but not far enough, and as they turn to walk away, it snaps off the bottom of their tube. So be careful taking your sample out, and be careful removing the spinner. The tubes are fairly fragile. And once you have the sample out, then you can come back to the console, to the computer, and click insert. Always leave the eject air off when you leave. So you should not be hearing the air blowing out the stack when you walk away. So once the eject off, you're ready to exit the program. So come up to File and Exit. And then once the software is closed, then you can log out of the Unix login. So at the very top on most logins is a green icon that looks like a running man. You click that, and you'll get a small window that gives you the option of switch user or log out. Always select log out. Switch user is not the option to use. So once you've done that, you're pretty much done. So make sure you take everything with you that you brought with you. A lot of cell phones get left, so that's a good thing to look around and take your stuff with you. And if you have any problems or questions, just let staff know.